All right, ladies and gentlemen, for Honors Chem 2, we're going to have a discussion today about strong acids and weak acids, as well as how to do Ka calculations. So this is where equilibrium comes back into play. I have a copy of the slides that you have in front of you. And just, we've got the acid and base. You have your quiz on Thursday. I'm not going to go back over all of this because I think you guys should be pretty well on your way with it. But I do want to go ahead and get started right at strong acids. So here we have a slide for strong acids. And it says some acids that fully ionize are not reversible and are said to be strong acids. In other words, you have many proton ions present in solution. Okay, so here's a few things. We've got, it says acids that fully ionize are not reversible, and it's because many H+ ions are present in the solution. Okay, so if we were to write this out, it would look like this. We have HA, and in the presence of water, it dissolves or dissociates into protons and the conjugate base part, the A-. So notice the arrow here is unidirectional. It shows that the reaction goes to completion. Okay, the dissociation goes to completion, so it mixes with water, it completely ionizes, it completely breaks down into H+ ions and the A- ions, okay, the cation and the anion. And something to keep in mind with these strong acids is that they are usually more hazardous than weak acids, and we'll see why, and it has to do a lot with the amount of H+ ions that are in solution. Okay, so here we see that strong acids are more hazardous because you have more H+ ions. All right. So again, completely dissociate or fully ionize, the reaction is not reversible. So you're going to have a, or I should put, you're going to have 100% ionization. Okay. Some of our strong acids that we may encounter include the following. We have hydrochloric acid. We have sulfuric acid. You have nitric acid. Boric acid. Okay. So when we say that these are strong acids, again, we're saying that they completely, fully, 100% ionize in the presence of water. For example, with sulfuric acid, if we put that in the presence of water, we're going to get 2 protons and a sulfate ion. Okay, so we have complete dissociation, complete ionization. Okay. And then we have weak acids, which are not strong. Okay, it says these are acids that break apart into ions and then recombine to form the original compound set up as an equilibrium. It says, actually it doesn't say it in here, but I'll write it in, that it has an incomplete ionization. Which means that we are less than 100% ionized. Okay. I don't know if you can see red and pink. Oh well. Incomplete ionization, it's less than 100%. And so if less than 100% of the substance is ionizing, then we are going to have fewer H plus ions present, which means that they are considered to be weak. And if you have fewer protons around, and the amount of protons determines the extent of how dangerous something is to work with. If you have a strong acid and you have as many protons around as possible, that's pretty dangerous. A weak acid has fewer protons, so it's going to be less dangerous to work with. Okay. An example of a weak acid would be something like citric acid, right?
The higher concentration of H plus ions, the most strong it is?
No. So strength and concentration are two different ideas.
They just said the number of H plus.
Yes, but concentration is entirely different.
Oh, okay.
Okay. In fact, I can skip ahead. I was going to do that tomorrow, but I can skip ahead to that here in a moment to clarify that statement. Okay. This is citric acid.
Oh.
So citric acid you have in a lot of like your foods or fruity beverages. Ascorbic acid, which is related with vitamin C. So some of those things are acids that we're able to ingest and eat. So if you think about it, weak acids we can eat. And so in water, you're not going to have complete ionization. So you have fewer protons to combine with other things and be less dangerous. Okay. Let's skip a moment and look briefly at strength versus concentration. Okay, so strength versus concentration are really two different ideas. So strength is going to refer to the extent that ions form, whether it's protons or hydroxide ions, if we're talking about a base. The Arrhenius definition. So strength is how much are you ionizing, right? You're strong if you have 100% ionization. So strong equals 100%, and weak is less than 100%. You can be anywhere from 1% ionization up to 99.9% ionization. The fact is we don't round up. So if you have 99.9% ionization, you're still weak, okay? Because you're not completely fully ionizing. So strength is, are you fully ionizing or not? Do you go to completion or do you set up an equilibrium? Concentration, on the other hand, refers to how many moles of solute there are per liter of solution. So you can have, say, hydrochloric acid and citric acid, and we can have a 3 molar solution of each. Okay, which one is going to be more dangerous to work with? HCl, right? It's a stronger acid. It completely dissociates. Citric acid doesn't. It's a weak acid. Put in other ways, it says in the statement, a high concentration of a weak acid can still be safer than a low concentration of a strong acid. Because even if you have a large amount of moles per liter of the weak acid, you still may have fewer protons in solution overall than you do of the strong acid that's of a lower concentration. Okay. It depends on what the math works out to be, but the generality there is that you can have that happen.
So, like, just looking at like hydrochloric acid and like the next one, how would you know which one is
strong?
Yeah.
So I gave the list on the other page of the 4 common strong acids.
Okay.
There's a couple others out there, but generally if it's one of those 4, it's definitely a strong acid.
Okay.
And if it's something else that we're less familiar with, it's probably a weak acid.
Ooh.
Okay. Ethan?
Oh, I'm not. Sorry.
But you are.
What?
But you are. Your hand is
my
in the
hand
air.
is raised. That's true.
So is it that you just don't care?
It's just comfortable.
making a reference there. Put your hands in the air like you just don't care.
Ah, yes.
Life changing is a visual.
That reference went right over my head.
And right into the wall.
Right in the wall.
All right. So does that make sense between strength and concentration? And that's actually a pretty big misconception that, that you have something like that. Pay attention. So yeah, big misconception there, which we had this morning, and that's fine because it allows us to talk about it. But a lot of folks think, oh, strength and concentration mean the same thing, and they don't mean the same thing. They're very different. Concentration is the mathematical part we did in solutions, like how many moles per liter, and then the strength refers to how many ions does it produce.
I like to think, like, we're trying to make this so that,
Probably more generally with properties of acids. Which, I forget, did it say which acid was part of, like, issue with it? Because acid rain, forget what acid rain is. Is it sulfuric acid? Like a very small concentration of it, but over time it can still corrode and eat away. All right, so let's continue on looking at weak acids, and we're going to focus on this slide with a lot more added to it here. But how do we measure acid strength? Okay, for acid strength, and by the way, I forgot to add this in the last one, and this will make sense. With the weak acids, if you have an acid with water, the idea is we still produce our H plus ions, but notice we have this equilibrium set up. So that means the reaction is reversible because it's not complete ionization. You get equilibrium. And it's the fact that it's equilibrium that we're going to take advantage of here in terms of acid strength. So it says here for acid strength, a Ka expression tells the relative strength of the acid. A larger Ka means that you have a stronger acid. In fact, we have with Ka, it's like K with equilibrium. So we're going to be setting up an equilibrium expression as part of this. Okay, and like it says, as Ka increases, the strength of the acid also increases. Okay, and think about it this way: if we look up here with this equilibrium, in terms of how acidic something is, we look at how many protons there are. So if we have a greater concentration, or I should say a greater quantity of the ions present as a result of the dissociation, then the strength of that acid will be greater. If we have fewer protons in solution, then the strength of the acid should go down. Right? Does that follow with what we talked about with pH? That is, hydronium or H plus concentration goes up, you become more acidic. And if it goes down, you become less acidic. And Ka is a measure of how strong that acid is. What?
The Ka expression of equilibrium.
Okay, so let's take a look here at an example.
On the notes, it says, like, the larger the Ka means the stronger the acid, but then the mean is more likely to reverse. How does that make it strong?
No, because what we're going to see here is that if we set up the equilibrium like we have here, is the greater the Ka, or the bigger the value is, this value, the hydronium or H plus, will be greater, the concentration of it. Okay. Plus, we are going to be relating strength to concentration, but relating concentration of H plus not necessarily the concentration of the acid itself. Okay, because you can have a certain concentration, like we said, of the strong and the weak acid, but they're going to dissociate in different ways. And so one will have a greater concentration of protons than the other. And the concentration of the proton is what tells us pH, which is going to tell us how strong the acid actually is.
Is Ka a measurement of strength?
Yep.
What's the difference between Ka and Keq?
So Keq is talking about equilibrium for any reaction or system at equilibrium. Ka is specific to acids that are at equilibrium, so weak acids. Tomorrow we'll look at Kb, which is for weak bases. So it's the same, it's going to be a similar context, but now we're going to do some different math with it. So at this point, I'd say pay attention to the math. If you don't pay attention, it's going to rock you pretty good. But if you pay attention, it should be okay. So, here's an example. Say we have an acid, just a generic acid, HA, and we dissolve it in water. Water is a liquid, of course. It's a pure substance. And HA dissociates into hydronium because water accepts a proton. So the Bronsted-Lowry definition, it accepts a proton to make hydronium, and then the acid donated that proton, so now we get A minus. So if we go and set up the equilibrium expression for this, the Ka would be equal to the concentrations of hydronium times A minus over the concentration of HA. Do we put water in there? It's a liquid. Do we put it in the expression? No, we do not. Okay. Water is constant, so we leave it out of the expression. Okay. So we're going to have an equilibrium expression similar to this for our reactions. So I want to show you some examples here. On the screen you have HF, which is hydrofluoric acid. And this one's been determined it's Ka, so it's a weak acid. Its Ka is 3.5 times 10 to the minus 4. Acetic acid has a Ka of 1.8 times 10 to the minus 5. So what we can see already is that HF is a stronger acid than acetic acid. Does that make sense? Because the Ka up here is greater. And what that means is that acetic acid is a much stronger acid than methanol, which has an order of 10 to the minus 16 for its Ka. So these are all weak acids, but because of these Ka or equilibrium constants, we can determine the relative strengths of them compared to each other.
Would you find the Ka of just like one acid? Would you plug into an equation?
Well, you would probably need actual concentration values for these, and then you could find the Ka. The way we're going to be going about this is that I'm going to give you the starting concentration in the Ka, which is a literature value. It's been determined already. And then we're going to solve for those, and that's going to give us some insight. Okay.
Mr. Myers?
Huh.
Is the Ka of a strong acid like one? We won't do Ka for a strong acid. And I don't want to explain it at this moment, but I think as we set up the problem in a moment, you will understand if we were to set it up for a complete ionization that mathematically we can't do Ka.
So for the equation that you just, like, for the example you just wrote out, are we solving for the Ka of just like A pretty much?
No, I'm going to provide you Ka. So stay tuned. You're on the edge of your seat, I can tell. But I'm getting there. The confusion will go away. Okay? Because I haven't given you a problem yet with the context. Okay? So here is a problem for some context. So it says calculate the pH of a 1.00 molar solution of acetic acid that's aqueous. Okay, and I'll tell you off the bat, we cannot do negative log of 1 molar. And the reason is because acetic acid is a weak acid. Okay, so you're writing that down. The first step in this is we need to write an equation for the dissociation. So if we have acetic acid plus water, which is a liquid, it's going to set up an equilibrium, and we're going to produce hydronium and acetate. What?
In the future, we're gonna have to know how to make these equations, figure them out. Okay, and is it basically the same concept as like it'd be like the Rancid Lowry? Okay, cool.
Okay, so here we write out the equation. And before I go any further, I want you to consider something. Okay, let's imagine for a moment that we start with 100 molecules of acetic acid. And at the very beginning, just like any equilibrium, you have a starting concentration. And before you start the reaction, do we have any products?
No.
No. So 0 products there and there. So we're starting out with 100 molecules of acetic acid. It's a weak acid, so it's not going to completely ionize. So let's say, for example, that we lose 1 molecule of acetic acid. Now, when acetic acid ionizes in water, we're going to make 1 ion of hydronium because we're donating the proton. So we gain 1 hydronium, and we're also going to have the acetate ion left over. Okay, so does that make sense that if we lose 1 molecule of acetic acid, we're going to gain 1 molecule of hydronium and 1 of acetate? Okay, so if we find the difference, we then have 99 molecules of acetic acid left over, and we've now gained 1 molecule or 1 ion each of hydronium and acetate. Okay, I know that overall that seems to add up to more than 100, but notice we're looking at ions now versus the other. Okay, so this concept where we have an initial quantity and we undergo a change, and then at equilibrium we have a certain amount left over. So this is the starting of an ice table. Quantity, we undergo change, and then we have what we are at finally. Please put the phone away. If you're not using your laptop for academic purposes, shut it down, please, or close the lid.
So it's E for N.
E is for equilibrium. So I is the initial concentration, C is the concentration change, and E is the equilibrium concentration. Okay, so we're going to use this concept going forward. Okay, so with this process in mind, we'd say that initially our concentration of acetic acid is 1 molar. And initially we have 0 of the hydronium and 0 of the acetate. Right? That's based on what we're given in the problem. And then we undergo a change where we're going to subtract some quantity of acetic acid. I don't know what that is, so we'll call it X. Okay? All I know is that we're not at complete ionization. It's a weak acid, so we're at equilibrium. We're giving up some concentration X of the acid, which means that we're going to add X to the other side. Okay. Again, I don't know what X is, but we're just keeping it generic.
Wouldn't the concentration of H or O we just have concentration?
The hydronium has no concentration to start.
No, I thought H2O.
H2O is pure, so it's constant. Okay. So then at equilibrium, our change is going to be 1.0 minus X. And then over here, we have X and X. Okay. So at this point, if we go back and write out our equilibrium expression, Ka is going to be equal to hydronium times our anion concentration divided by, and I shouldn't say A, I should say C2H3O2. It's a very long line there. And then on the bottom is our acid. And what we're doing is we're going to plug in all of our equilibrium values. And up above in the table, we saw that the Ka for this acid was 1.8 times 10 to the minus 5. And we say that this is equal to our hydronium we found to be X. Our acetate ion concentration at equilibrium is also X. And our denominator for the acid is 1.00 minus X. So we have the start of what could be a quadratic equation. Bum, bum, bum. But we're not actually going to do the quadratic equation. Jackson.
Where did you get the 1.8?
If we go back to the top here, Ka of acetic acid was 1.8 times 10 to the minus 5. Nope, it'll be provided to you. I'm not that mean. Okay, so this example, we can rewrite this and actually say, sorry, we can simplify this and say that whenever X is much less than, oops, our concentration of HX, in this case it's our acetic acid, we can actually ignore right there because the difference is going to be pretty darn insignificant. And so by assuming this, which we're able to do, we get away from having to do the quadratic equation.
Where's the HX?
HX is a generic acid. In this case, it's acetic acid. Okay. So all I'm saying is if X is much less than this concentration here, 1, which it is, I'm telling you it is, you have to believe me, then we can just cross it out and say the difference is going to be fairly insignificant.
So you are going to give us the little scientific notations bit?
Yes.
Okay.
So we can rewrite this here. And if we take 1 and multiply it on both sides, we get 1.8 times 10 to the minus 5 equals X squared. Okay. So then your goal is to take the square root of both sides, and that's going to give us a value for X. Go ahead and calculate what X is.
Okay, what do we get for X? Sure.
Then 4.24 times 10 to the negative.
All right, and that's molar. So is that what you guys got? Okay. So remember, initially they said, we want you to find and calculate the pH of this weak acid solution. So remember that pH is equal to the negative log of H plus or hydronium. What you guys just found with this X here was the X right there, which is hydronium. So by doing all that work, we found what our hydronium concentration is at equilibrium. So we can plug that into our equation here and say the negative log of the 4.24 times 10 to the minus 3, what does that come out to be? You guys got 2.37. Okay, so the pH of this weak acid is 2.37. Notice if we had just done the negative log of 1, because that was the concentration of our acetic acid, our pH would be 0, which would suggest that it's an extremely strong acid. But we already know for a fact that it's not a strong acid, it's a weak acid. So it should have a pH that's a little bit bigger. Okay. Furthermore, whenever we do negative log and we say, oh, it's a strong acid, so we just plug it in, we can, because the idea with our equilibrium expression up here is that if this was a strong acid, if we started with 1, we would finish with 0, right? We would lose all of it, which means over here we would gain it entirely. So we would have a Ka that is 1 divided by 0, which doesn't work mathematically. So we don't use Kas for strong acids or strong bases. It doesn't work mathematically. It's undefined. Okay. All right, let's see another example. Okay. In this example, it says, what is the pH of a 0.01 molar benzoic acid solution? And the Ka of benzoic acid is 6.5 times 10 to the minus 5. And for simplicity's sake, we're going to call benzoic acid HX because it's a lot easier to write out. Okay, so our first step, once you jot the question down, is you need to write out that weak acid equilibrium equation. Not the expression yet, but the equation for the reaction. Okay, you guys have the question or problem right now?
Yeah.
Okay, so we're going to call benzoic acid HX. So our first step is to write the equation. We're going to have HX, and it's going to go up against water. because it's a weak acid, it won't completely ionize, so we set up an equilibrium. What we end up producing is hydronium and X minus. Okay. Okay, so initially, what is the concentration of HX? 0.01 molar. And what's our concentration of hydronium and X minus? Okay, 0 for both. So then our change, we're going to say we're going to lose X. We don't know what X is. It's an algebraic variable. All I know is we're going to lose X. And if we lose X, we're going to have X amount of hydronium produced because the base accepts the H. So we show plus X on both sides. And so at equilibrium, the change, or after the change, what we have left is 0.01 minus X. So that quantity is left over of our acid, and then we have X available for both ions. Okay, these are our concentrations at equilibrium, which is going to allow us to set up our Ka expression, which will be hydronium times X minus over the concentration of HX. And based on the info above, we're provided with a Ka value, 10 to the minus 5. So 6.5 times 10 to the minus 5 equals our concentration of hydronium, which is X, and our X minus is X. So together, you see how that's X squared? Can I make that jump okay? And then on the bottom, we have 0.01 minus X. And again, we're assuming that X is much less than our concentration, in this case of HX, of that 0.01.
How do you determine if X is like too significant amounts left?
It is. I'm telling you it is.
Got it. Cool.
It is, because I said so.
Will it be like that in the future?
Yes.
Just gotta know it.
You have to know that we're not going to include the minus X. I mean, we can do the quadratic equation and quadratic formula to solve. It's more work, and you're going to get a very similar result, which suggests that the X here is going to produce an insignificant change.
Okay.
Okay. So in doing that, we can multiply both sides by 0.01, which would be 6.5 times 10 to the minus 7. And that equals X squared. So if we take the square root of both sides, that's going to allow us to figure out the value of X. Which is going to come out to 8.06 times 10 to the minus 4 molar. Okay, and that value of X is also then equal to the concentration of our hydronium. Okay, and we know that because above in our ice table, we said that X is our equilibrium concentration for hydronium. So then we're going to go one step further here, folks, and recall that pH is the negative log of hydronium. And if we plug this value right into there, we're going to get a pH
of 3.09. What do you guys think? Tough but doable?
Unbelievable.
Kind of
I
what?
have one question.
What's your question?
So why do we never do anything with like the denominator of the equation? Like the 0.01, like it always just like goes away.
It didn't go away. We multiplied both sides by the value to solve for x.
Wait.
This is-
It went to -7.
Did you pass?
Any other questions? Yeah, be sure to like, comment, and subscribe. Smash that subscribe button.
Oh, you know I did that.
So those type of equations are good for homework.
By the way,
Yep.
Mr. Myers, just to clarify, we were live streaming.
Were you?
Yes, we were.
Do you have any homework?